So these ligands are kind of interesting. Again, a ligand is nothing more than a Lewis base, and every Lewis base has one lone pair at least that can bond to the central atom, to the Lewis acid's metal center. All right, and they classify ligands according to dentate, and apparently dentate means tooth in Latin, and each tooth is like a lone pair on the atom that can make a connection to the transition metal. So if you hear about a monodentate ligand, that has one tooth. It has one lone pair that can bond with the central metal. Likewise, bidentate would be 2, tetradentate would be 4, hexadentate would be 6 teeth, and polydentate just means 2 or more donor ligands. Now, a chelating agent is a term you may have heard of before. Chelating agent is just a ligand with 2 or more teeth, 2 or more places to bond to metals. And they can render metal ions actually inactive. They essentially can pull them out of solution and make them do something else. Phosphates are a great example of how they can tie up calcium and magnesium ions in hard water, so it keeps them from interfering with detergents, stuff like that. We'll talk a little bit more about this in a little bit. But anyway, this teeth thing is really fascinating. And again, each tooth, 1, 2, 4, 6, whatever, is essentially a lone pair on the Lewis base. Monodentate ligands have only one lone pair that's accessible to the transition metal. And water is a great example of this because water has a lone pair. It has 2 lone pairs, but because of the hindrance of the geometry, only one of them can react at one time. So these aqua complexes are basically all the transition metals in water. You've got the water connecting to the transition metal, and you're good to go. This is the ion dipole force on one level, but it's also a pretty strong force. There's lots of monodentate ligands beside water, though. Cyanide is actually monodentate. Now notice that it has an ionic charge, but it still has only one accessible lone pair, usually the carbon, sometimes the nitrogen, that can connect to the metal atom. Ammonia is neutral. It has one lone pair that can connect to the metal. The next one, NO2 minus, is nitrite. Nitrite is monodentate. So is SCN minus, thiocyanide. Hydroxide, X is just for halides, carbon monoxide, oxide, lots of examples of it. So very commonly you'll see ammonia and water as ligands, monodentate ligands. Sometimes you'll see other ones. So CONH3 would have 6 monodentate ammonias. Iron with FeSCN6-3 would have 6 thiocyanide surrounding it. The picture of the beaker on the right is an example we talked about when we talked about complex ions. That's copper, and the bottom and the top versions right there show the ammonia and the waters. And initially copper, when you place it in water and it dissolves, it makes that CuH2O6 2+. So the water is acting as a monodentate ligand. They surround the copper and you're good to go. On the other hand, if you had an excess of ammonia, we saw how the copper can turn that kind of dark blue color, which is just wild. The ammonias are kicking the waters out. So you end up with ammonia pushing the waters out. You have a different complex ion, and as you can tell, the color is quite different too. Bidentate ligands are bigger than monodentate ligands because a bidentate ligand has 2 accessible lone pairs, and they must be a couple of atoms apart from each other. So here are just some examples of some bidentate ligands. One of them is oxalate, which is C2O4 2-, and the structure of it is listed in the upper right-hand corner right there. Oxalate is often abbreviated OX. Now earlier I did show a structure that had this EN in it. EN stands for ethylene diamine, and this thing right here in the middle is ethylene diamine. Now in both oxalate and ethylene diamine, the important part is that there's going to be at least 2 places to make bonds with metals. So in ethylene diamine, those 2 red stars right there, that's where the metal will bond. On the oxalate, it's going to happen on 2 of the oxygens on the same side of the molecule. The other 2 would be too far away. They couldn't make bonds with it. The wildest of these is orthophenanthroline, or OPHEN as it's abbreviated. You can see it's kind of got that wild ring structure down there. Again, the red stars there show the lone pairs where you can be like a Lewis base, and those two places will connect to the Lewis acid and do some really wild chemistry. Most of these complexes will only handle octahedral, which means 6 coordinates around them, or 6 places that the bases can connect to the Lewis acids. So usually you won't see more than 3 of these bidentate ligands. So COEN3+, that would be 3 ethylene diamines connected to the cobalt. And since each ethylene diamine has 2 teeth, that means that cobalt is in a 6 coordinate or octahedral coordinate. It's cobalt 3+, ethylene diamine is totally neutral, so kind of interesting. Now, on the other hand, the next one down there is an oxalate. Now, oxalate has a charge. It's a -2 charge. So if you have 3 -2 oxalates and the overall charge on that molecule is -3, that has to be a chromium +3 to make that happen. So in the second example, that chromium +3 has 3 oxalates around it. Each oxalate binds at 2 places. That's another example of a 6 coordinate or octahedral complex. And then the last one, orthophenanthroline, is a big, big molecule. So sometimes you can only fit one of those around there. That iron one is an example where there's 4 ammonias and 1 phenanthroline that connect around the iron to make that happen. Orthophenanthroline is neutral. There's no charge. So in that complex with iron, the ammonia is 0 charge. The orthophenanthroline doesn't have a charge. That +3 reflects the charge on the iron. Here are just some examples. This is an example that I found with 3 orthophenanthrolines. And if you look at that animation there, you can see they're like little propellers. Sometimes they call this propellerane, apparently. I don't know. It's pretty crazy. But in the upper right-hand corner, I want to introduce this. This is called ribbon theory. And sometimes when you get to so many atoms, it's better to just write those ribbons right there. So in ribbon theory, you show the connecting atoms usually, which are in this case nitrogen, and how they're connected to the central atom, which in this case is cobalt. This is an example of having 3 ethylene diamines, 3 En molecules that are surrounded to the cobalt. But you can see how the ribbons make it a little bit easier to see the geometry. The iron one there on the left-hand side and the video of it are kind of cool, but they're also kind of confusing sometimes to see how the atoms are arranged. Another compound that's bidentate is called dimethylglyoxime. And dimethylglyoxime is something that you will use, or maybe you already have used in lab. In the QA3 lab, the test for nickel ion is when you add the dimethylglyoxime to it. And you end up making an NIDMG2 molecule. And here's an example of 2 of my former students. They solved for the NIDMG2. They had nickel in their compound. Woohoo! Anyway, it's just another bidentate ligand, which is kind of cool. Now, in this picture here in the lower middle, the nitrogens are connecting to the nickel, all right? That's the bidentate part of this dimethylglyoxime. But what is kind of cool of dimethylglyoxime, like this oxygen right here is connected to the hydrogen on the OH on the second one. That's a hydrogen bond. The OH hydrogen's connected to OF or N, is connected to another OF or N. That actually helps to stabilize this molecule. And in the lower part, then, this hydrogen, which is connected to the same molecule as the N's I circled, has a hydrogen bond connected to that oxygen. So it's a pretty cool thing. But more importantly, it's just an awesome color. It looks like, I don't know, fruit juice or something. I don't know. Don't drink it. Don't drink anything in my lab. However, it is kind of a cool thing, and I hope you'll see it too. Ethylene glycol is an ingredient that sometimes people put in their radiators, and ethylene glycol has that structure below. How would you describe the dentate character? And you can see there's mono, di, bi, dentate, tridentate, etc., etc. Zero dentate, by the way, isn't a word. But anyway, the number of lone pairs is what you're looking for. So in this molecule, the OH on the left and the OH on the right both have lone pairs. So that is potentially a bidentate ligand. And they're far enough apart, all right? Like there's 2 carbon atoms between the OHs that I'm pretty sure that ethylene glycol would be a bidentate ligand. both of those OHs would be capable of forming a Lewis base interaction from them. And they're far enough apart that I think they could wrap around the molecule and you could get them set up like that. So again, look for number of lone pairs. They got to be separated a little bit by a couple of atoms. This will be bidentate. EDTA is a commonly used polydentate ligand, which means many teeth in it. And EDTA is pretty fantastic. It's used in biology a lot, which is pretty cool. EDTA is great because it makes one-to-one complexes with most of the metals, except for group 1A. So what that means, for example, if I put EDTA with chromium, it would take one EDTA to bond with one chromium, 1-to-1, all right? Now, it doesn't do very well with group 1A, so sodium, potassium, lithium, EDTA doesn't work very well. However, all the other metals, in my opinion, it works really well, and it can pull the metal out of a solution if you don't want the metal to be there. And it tends to form then stable water-soluble complexes that can be extracted from the remaining material. They have high formation constants, which means they form very readily, which is really cool. It's also called a primary standard, which means you can use it basically right out of the box, all right? Some chemicals you have to heat up or dry them off before you can use them. Boy, not EDTA. EDTA is good to go. But the best part about EDTA is that EDTA was actually involved in the very first Blade movie. Now, you don't have to like any of my movies to do well in my class. I'm going to let you know. However, the Blade was a superhero. He was essentially a good vampire that killed all the bad vampires, and he used EDTA to kill some of the bad vampires. It's really a fun series of movies if that's your thing. If it's not, don't go rent them and stuff. I don't recommend them. That's Wesley Snipes right there. It's kind of cool. Anyway, I usually show like a little video of Blade, but I'm not going to do that because YouTube would zap me on that. Anyway, check it out if you get bored. EDTA makes its appearance. This is the structure of EDTA. EDTA's full name is ethylene diamine, which is similar to the EN group we saw earlier, but it's ethylene diamine tetraacetic acid. So instead of having NH2 at the end like ethylene diamine did, each of the hydrogens has been replaced on the end by a CH2C double bond OO group, and those can have acid H plus on them, and right now we're seeing the non-protonated version. But the important part for us is not about that. Each of those lone pairs is capable of bonding to the metal. So each of those red stars is a place where bonding can happen. So all of the O's on the end with red stars and the two nitrogens in the middle can make a connection with the metal. So it literally wraps around the metal. So check out that cobalt EDTA -1 species in the upper right-hand corner. The ribbons are used to show just the connection points. The red atoms are oxygen and the blue atoms are nitrogen, and it literally just goes all the way around, which is pretty cool. So it wraps itself around the metal. It then can be extracted from whatever system you have, and the metal can be removed. These are the log of the equilibrium constants for forming the EDTA metal compounds. And so what you would do here to find the actual equilibrium constants is you would go 10 to the power of those numbers. That would give you the actual K value. So these are huge, all right? These are really, really big equilibrium constants. And that just shows how ready the metal EDTA things are going to form. Now, again, notice there's no sodium, potassium, lithium on here. Group 1A, it doesn't work out too well, but magnesium and calcium and all those kind of things, as well as almost all the transition metals, to my knowledge, they're extracted with EDTA really, really well. There's other chelating agents as well. Porphine is an example of one that's found in nature. It has the 4 nitrogens right there, and if it's done correctly, each of the nitrogens can bond with your central metal. Myoglobin is an example of an iron in the middle that can store your oxygen and move it around, which is kind of cool. There's oxymyoglobin and oxyhemoglobin, which are the oxygenated versions of those compounds. So pretty cool kind of stuff. And again, these things are really important. They allow oxygen to be transported. They allow bad metals to get out of your system. Lots and lots of uses. This is just a silly meme. This is hemoglobin. Hemoglobin is responsible for transporting oxygen through our bodies, but hemoglobin, if it sees carbon monoxide, is much more attracted to carbon monoxide, and it makes a bond which is almost unbreakable. So if you happen to be around carbon monoxide, boy, be really careful, because if you breathe it, carbon monoxide bonds with your hemoglobin and it doesn't let go. So you can't get oxygen to your body anymore. It basically suffocates you. So that's kind of a stupid science joke there. But anyway, you get the idea. Stay away from carbon monoxide and you'll be okay.